here's the flow metering data that you took at Crowden Great Book on the 8th of October. You've got the distance measurements that are then turned into areas, and then you've got a set of triplicate velocity measurements that you turn into an average, and then you multiply the velocities by the areas to give you the discharge in each panel, and then sum them to get the total discharge. You also need to carry the errors. So we've got the width and the depth. I've assumed that there's a 1 centimetre error on any of the measurements, the distance measurements. The error's probably less than this, but when the water's turbulent and you're measuring the depth, the water moves up and down a bit. And similarly, when you stretch the tape across the river, it's not exactly vertical. If it's not exactly horizontal, then there's errors because of that. So I've put down an assumed error of 1 centimetre on each of these measurements. It's not as a percentage of the measurement, it's actually a 1 centimetre error. And largely that's also because of the resolution of the tape as well. Anyway, so multiplying the width by the depth will give you the area. However, it's a little bit more complicated because of the shape of the channel, and that's plotted over here. So these charts are plotting the width against the depth and reversing the y-axis, so it actually looks like a channel. And you can see then that the areas of each of the panels will generally include a rectangular area and a triangular area underneath. So the formula that's in there is just working out the area of a rectangle and adding the area of a triangle. You don't need to do that, that's already written in for you. The errors that are worked out on those are a standard way of working out an error when you multiply two numbers together. So you can have a quick look. In the heart of it, you have the error, so C16 is an error divided by the number itself. So C16 divided by B16, so the error divided by the number squared plus the error divided by the number squared, and then we take the square root. So similar to what you do when you're adding two errors together. And then the final thing is that you multiply that whole amount, which is called the fractional error. You multiply that by the resultant quantity. The resultant quantity, F16, is the area. So that's the standard way of multiplying, carrying the error when you multiply two numbers together. Now in fact, in this case, it should be a little bit more complicated because you're not just working out the area of a rectangle, you're also working out the area of that triangle as well, but I've disregarded that in this case. It's minor, you don't need to go into that. But you'll need to use this formula again when you multiply the area by the velocity. So you've got three sets of velocity measurements that were notionally taken at exactly the same places in terms of width and depth. They aren't exactly the same number, so that's partly to do with not being able to locate in exactly the same position with regard to width and depth, and also there may be some slight temporal variability in the velocity. Rivers do actually pulse. It's not necessarily to do with the discharge changing overall. There's no extra water entering the system, but they actually pulse. Anyway, there's some error, and you've been able to detect that by making multiple measurements of the discharge. So the first thing that you need to do then is to work out the average velocity. So we'll enter average. It's the average of these three numbers. And copy that down. So you've got your average velocity. The error on your average is the standard error of the mean. So in order to get that, we need to do the standard deviation. It's not standard deviation P, it's just standard deviation, because these are a sample of all the possible measurements you could have made. Standard deviation of these three numbers multiplied by a d value, but in fact it's a small sample size, it's a t value. We get the t value for using the t inverse function, and the arguments that it requires are the probability, which is 0.05. We're working at 95%. The degrees of freedom is n minus 1. N is 3, so n minus 1 is 2, so we'll put 2 in. We need to divide by the square root of the number in the sample, so divide by 3 raised to the power of 0.5, that's the square root of 3. Into that, copy it down. Now we can work out the discharge. The discharge is going to be the area, meters squared, multiplied by the velocity in meters per second, which will give us meters cubed per second. So it's equal to the area multiplied by the velocity copy that down, and then the velocity, the discharge across the whole stream is the sum of the discharges in each of the panels, each of these panels. So we just need the sum of those equals the sum of these discharges. 0.31. Now we need to work out the error on each of these discharges. We can put in a couple of brackets to start with, but we can come back and make sure the brackets are right as we go along. We're going to take the error on the area and divide it by the area itself, and square that, then add that to the error on the velocity divided by the velocity, and square that, and then we can put in another pair of brackets and take the square root. So that's very much as you'd do if you were just adding two errors together. That's the fractional error. We need to multiply the fractional error by the resultant quantity. The resultant quantity is the discharge itself. So that's the discharge multiplied by this, which is the fractional error. Division by 0 because the 0 is in there, but if we copy it down, we get the errors, and we should put those to 3 decimal places as well. Then we need to work out the total error, so we need to sum the errors on each of the panels together, and when we're summing errors we square them and then add them together and then take the square root. The easiest way to do that is to put in another column where we'll put in the error and square it, and then we can put the sum of the squared errors and take the square root, raising that to 0.5. Again, putting it to 3 decimal places. And there we go. We've got a discharge of 310 litres a second, or 0.31 metres cubed a second, with an error of plus or minus 0.014 metres cubed per second, or 14 litres a second. The mean that you've worked out will pop up in this little table up here, and you need to work out the discharges and the errors on those discharges for the two other sets of data as well, and the means will then pop up in this table, and then you can work out the average of the three means and the standard error of those three discharges. So you'll have worked out a discharge and the error from within the method, and then here you're comparing the three different discharges and working out the standard error between those three measurements. Then you can compare that sort of flow metering discharge calculations to the same three sets of dilution gauging that you did, and consider you can't consider accuracy because we don't know what the discharge in the stream was. In this case, we don't have a standard against which to judge it. The discharge in the stream is unknown, but you can consider the precision, and then also if there's a discrepancy between the flow metering and the dilution gauging, if that has anything to tell us about hyperrheic flow. I think it's worth having a look at these diagrams, which are the shape of the channel, to see how regular that is, how comparable it is between sets of measurements.